Now, like in the other spaces, we are going to define for a given divisor, specified divisor A, we will consider the set of all weil differentials which vanishes on the other space of this given divisor A plus F. And indeed, this space can be interpreted as the orthogonal complement of the other space of A plus F, or the annihilator in the dual space of the other space. And indeed, we can also see that this forms a subspace of the weil differentials. So that means for given any divisor A, the weil differentials of this divisor A forms a vector space over K. So that means this is also closed under addition and closed under scalar multiplication. More explicitly, for any non-zero constant C and the weil differential from the set of space of weil differentials of A, we want to see that C times omega, the multiplication will be the same multiplication we defined when we show the weil differentials forms a K vector space, because that means for any alpha plus x, we define this scalar multiplication as the weil differential of the multiplication of alpha plus x by c. And indeed, since this sum forms a vector space over K, we know that this multiplication also belongs to this vector space. And we know that W vanishes on this sum. That means the image of this element is going to be 0. And indeed, this shows us C omega is also weil differential vanishing on this sum. And that means this is closed under scalar multiplication. And similarly, if you consider two weil differentials which are vanishing on the specified divisor, the other space of the specific divisor A plus F, and we want to see that for any element in the sum, their image under this addition of the weil differentials, which have defined as the weil differential of this element and the omega 1 of alpha plus x plus omega 2 plus alpha plus x, is going to be 0, because we know that W1 vanishes on this space, so that means the image of this element under omega 1 is going to be 0. And since W vanishes on this vector space, the image of every element is going to be 0. And this gives us the desired. And indeed, even though the space of weil differentials forms a finite infinite dimensional vector space, now we see that the space of weil differentials of a divisor, specified divisor A, indeed have the same dimension of the quotient space of the adele space over the adele space of the divisor A plus F. So that means, briefly, the dimension is going to be, again, index of specialty of the divisor A. And indeed, in order to see that, if we recall the definition of the weil differentials of a divisor A, that means these are the weil differentials vanishes on the adele space of A plus F. Indeed, so that means this vector space, the sum of this vector space lies in their kernel, or indeed, we can find a one-to-one correspondence in a canonical way between the k-linear forms from this quotient space to K. So that means their kernel still contains this sum of vector spaces. And if we refresh our knowledge from the linear algebra, if we have finite dimensional vector space U over a field K, the space of linear forms from itself to its space field has the same dimension with given vector space U. So in this case, if we consider all k-linear forms which are defined from this vector space to K, so that means it has dimension of this vector space, which is indeed the index of specialty as we computed in theorem 1.4, 5.4. And as a corollary of this lemma, indeed we can see that, I mean, as a simple consequence, indeed, we can see that the space of weil differentials are, weil of space, the space of weil differential is a non-trivial space, because if we choose a divisor of degree less than or equal to -2, dimension of the weil differentials of this specific divisor A is going to be index of specialty, and by its definition, it's going to be dimension of its Riemann-Roch space minus degree A plus G minus 1. So if the degree is negative, we know that the dimension of Riemann-Roch space in this case is 0. And in this, if the degree is less than or equal to -2, so that means minus degree is going to be bigger than or equal to 2. Indeed, this quantity is bounded below genus plus 1. And we know that genus is positive, bigger than or equal to 0. We can claim that for such a divisor, the space of weil differentials of the divisor A has dimension at least 1. And for every divisor, its space of weil differentials form the subspace of the space of weil differentials, whose dimension. So that means this is not going to be, this cannot be a trivial space, and this shows us omega F cannot be trivial space. So this is not a trivial space. And moreover, I mean, okay, they are vector space over F, but the most important the information in that we will see that the space of Weil differentials forms also vector space over the function field F, and its dimension is going to be 1. And in order to see that, first we need to define a multiplication of a Weil differential by a function F, because we want to say that this forms a vector space over F. And to this end, we will define this multiplication as a K-linear map from the space of Adas to K. That means which maps, this is also going to be Weil differential indeed, we will see it later, but this maps to Adas to the image of x times alpha. So here indeed we multiply the other alpha by x component wise, and we take its image under omega. And indeed this is also a similar definition how we define the scalar multiplication for the Weil differentials. And now we want to see that this indeed this map, this K-linear map is also Weil differential. So that means we need to see that it vanishes on some divisor. So that means our claims that x times omega, which is defined in this way, is also a Weil differential. In fact, if omega is a Weil differential which is vanishing on the other space of A plus F for some divisor A, our claim is to see that XW vanishes on the other space of the divisor A plus the principal divisor of x, the function x, we consider in this multiplication, plus f. So indeed, what we want to see that if we take any element from this sum, its image is going to be 0 under this K-linear form. So that means xw of A plus z by the definition of this multiplication by f, it's going to be omega of x plus alpha plus z. So that means alpha x plus z times x. And indeed what we want to see that, okay, this is f, and if we can see that this alpha x is element of the other space of A, we can see that this is indeed 0 because omega vanishes on this sum of vector spaces. And in order to see that, if alpha plus z, if alpha plus z in this adele space, so that means alpha is chosen from the adele space of A plus the principal divisor of X. That means for any P, its valuation at P is bigger than or equal to VP of A plus principal divisor X for all places in P. More explicitly, VP of alpha P is bigger than or equal to VP of A minus VP of X, and just removing this valuation on the right hand side, VP of alpha P plus, this is going to be minus, plus VP of X is bigger than or equal to VP of A. And indeed, this shows us alpha plus X in the adele space of the divisor A, just by the definition in terms of the discrete valuation maps of the places for all places P. And indeed, this shows us its image is also under, its image also is going to be 0 under omega. And indeed, we show that X omega is also a weil differential, vanishing on particularly, which is determined by the divisor.